Well, hello everyone. This is Rebecca Dallin, Assistant Superintendent of Stormwater Quality here at the City of Oklahoma City. I would like to officially welcome everyone to the final edition of our 2022 monthly series. We will begin the main presentation momentarily, so I want to provide some information to help enhance everyone's experience during today's program. In order to reduce background noise, we ask that everyone keep themselves muted during the presentation. If anyone has any questions during the presentation, feel free to type them into chat. Chris Stewart is helping me out today, and he and I will be monitoring chat for questions, and we'll have our guest speaker answer as many questions as we have time for today. If anyone would like to receive a certificate of attendance for today's webinar, please send me an email to request it, and Chris will put my email address into chat so you'll have that handy. Each of the presentations in this webinar series will be available within a week or so after the scheduled webinar dates on our website under Stormwater Workshops. And the section where these webinars are posted is called the 2022 webinar series. And of course, today's session is the December edition. Chris will be posting a link to that website where you can find those presentations toward the end of today's program. And spoke with our public information person today. We had a luncheon meeting today for APWA, the Public Works Association. And she said that she would not be available until probably next week to get that posted. We're going to try and do it later today, but I'm not sure I can get the video to her because she's going to be teleworking. Anyway, next year's webinar series is changing to every other month. Announcements and signups for next year's series are being released via our emailed newsletters this month, and we've already kind of got those started. So if you haven't seen that yet, make sure you get registered for our newsletters. The bi-monthly sessions are going to start in February. Be sure to sign up for the new series since registrations are not carried over from year to year. And of course, if anyone has any questions at this time, feel free to type them into chat. But without further ado, Chris, would you please play the very short welcome series, our webinar series welcome presentation?
Good afternoon and welcome to our monthly Stormwater Quality webinar series. We have enjoyed providing opportunities to learn how you can help keep our local waterways clean. Remember, we're all downstream from someone else, so we all need to work together to protect our waterways. During this series, you have had the opportunity to hear from some of our own stormwater quality staff, as well as several guest speakers. This month's presentation will feature a guest speaker from Oklahoma State University to round out the series. Dr. Jamie Schuessler will be sharing her presentation entitled Improvements to Erosion and Sediment Control Design Through Performance-Based Testing. We hope to see you again next year, so be sure to register once you get one of our e-newsletters. As we briefly mentioned, each of the presentations should be available online within a week or so after the presentation is aired live. It will be posted to the workshop section of our Stormwater Quality website. We'll post a direct link to that page into chat toward the end of today's program. The 2022 series will only remain available on our website until we begin our 2023 series, so if there's anything you still wanted to view, be sure to do that soon. If you haven't signed up already, please do so now by pointing your phone's camera at the QR code for the newsletter that you're interested in. The only way to sign up for either the construction or industrial training and education newsletters is via a direct website link or these QR codes. These options are both hidden in the email service site, GovDelivery. These two newsletters are the main way that we announce upcoming training, webinars, and workshops, so be sure to sign up. The quarterly newsletter is the third QR code, and it provides overall information about what we're up to. You can find this one on the GovDelivery website. If you've missed any of these codes, be sure to send Rebecca an email and she'll send you the direct website links. Next year's webinar series is changing. Announcements and signups for next year's series are being released via these newsletters. Some of our presentations will be live and some will be pre-recorded. We do our best to provide as much detailed, accurate information as possible while also working with the presenter's strengths and their schedule. We live and work in a beautiful community here in Oklahoma City. For more information on stormwater, what we're up to, and local regulations, be sure to visit our website.
All right, Up next is the main presentation for today's webinar. Today, we're going to hear from Dr. Jamie Schuessler from Oklahoma State University. Dr. Jamie Schuessler joined the School of Civil and Environmental Engineering at Oklahoma State University as an assistant professor in August of 2022. Prior to her appointment at OSU, she received her doctorate in civil engineering from Auburn University. Her research focuses on stormwater management, specializing in erosion and sediment control. Her work aims to find implementable solutions to manage increased stormwater runoff and sediment loads from construction, urban, agricultural, and reclamation sites.
Hello, thank you for that introduction. I'm so happy to be here with you all today. I will be sharing my screen. Give me just a second to get the presentation pulled up. Okay, are you able to see the presentation?
Yes, I can see it clearly.
Okay, thank you so much. So as mentioned in the introduction, I will be presenting on improvements to erosion and sediment control design through field monitoring and performance-based testing. So just a little bit about me. I moved to Oklahoma in July of this year, and I am very happy to have just completed my first semester as an assistant professor here in the School of Civil and Environmental Engineering. My first semester, I completed teaching stormwater management and green infrastructure, and in the spring, I'll be taking on hydrology. So I've been really impressed with our students here and happy to be spreading the world of stormwater. Prior to joining OSU, I did my PhD at Auburn University in Alabama, and I did my master's at Iowa State University, and then my bachelor's degree at West Virginia University. West Virginia is where I am originally from. Now, while I've kind of been all over the place doing my work in stormwater, one thing remains consistent, and that is I really sink my teeth in wherever I go. So this was my first research project in Iowa. I was monitoring sediment basins and got myself stuck. So I say my claim to fame is that I had to be rescued from my first research project, but I've gotten through the thick of it, and now I'm happy to be here at OSU, starting in stormwater research in the state. Now, I'm sure we all know at this point, by attending the webinar series, that stormwater is a pollutant source that actually is continually getting worse, and that's because we're constantly changing the landscape to match our needs. And with that, we're doing a lot of construction and opening up and disturbing our land. Now, our construction activities can often drive and accelerate erosion rates and thus the sediment delivery to our waterways. Now, erosion rates in construction are 1,000 to 2,000 times that of a naturally vegetated area and about 20 times that of agricultural lands. Now, the U.S. EPA identifies sediment along with nutrients and heavy metals as one of the most widespread pollutants that are affecting the beneficial uses of our nation's waters. Now, this is when we start talking about water impairment. And impairment indicates that there are limitations for our recreational use, consumption, and support of aquatic life. Now, sediment pollution is our main pollutant here in the state of Oklahoma. Now, today I will be focusing in on the erosion and sediment control techniques that we may be able to use during construction to try to mitigate this and minimize our downstream impact. Now, the U.S. EPA has the National Pollutant Discharge Elimination System, and there are several areas under this program, one being construction and then also our industrial and municipal programs. Now, within the construction general permit, or the OKR 10, as we call it here in Oklahoma, we are required to have a stormwater pollution prevention plan, and this includes the design, installation, maintenance, and location of our erosion and sediment controls that are used during earth disturbing activities. However, there's a big divide when it comes to the design, installation, and maintenance. Designs may differ from state to state, regionally, but they also may differ within the state, depending on which municipality you're operating in. Now, a lot of times we're seeing that even if the designs are quite good, we might have a problem with improper installation or lacking maintenance. Many times, erosion and sediment controls are implemented based on the rule of thumb or what's been done in the past. However, they lack performance data and field-based testing. And so that's where I have really come into the field and taking on some of this as research. Now, I started a research project with the Iowa DOT back in 2018, and this project aimed to assess the current practice of erosion and sediment control, and then also make modifications that may improve the performance. Now, the first step in this was to compile and catalog practices that were applicable during DOT construction, then install and evaluate these practices and be able to characterize their performance, and then make observations on any shortcomings and try to develop modifications to address these. So if you're interested, there is a QR code here, and that links to the full report of this project that I'll be talking about today. And this QR code will also be available later in the presentation. This specific project for the Iowa Department of Transportation was called Field Monitoring of Erosion and Sediment Control Practices and Development of Additional DOT Guidance. The very first thing we did with this project was take several site visits. We took site visits to various projects throughout the state and cataloged what erosion and sediment control practices were the most reoccurring in between each project, but also problematic. And so some of the catalog practices that we came up with are shown here in this picture, including silt fence sediment barriers, ditch checks, and this included both silt fence and wattles, and then finally our detention practices, or what we were calling sediment basins. So here you can see we have an example of our ditch checks here on the center line. We have our sediment barriers here on the perimeter and down just a little bit. And then we also have several sediment basins all along this channel. Now you'll see there's one back here, there's one up here. So several different practices that are used in a single span of DOT construction. So the first one I will be getting into is talking about those silt fence sediment barriers. So here, when we took a walk along the site, we saw a lot of sediment capture behind our silt fence. However, lacking maintenance caused a lot of these T-posts to deflect. We had silt fence laying on the ground, which was a pretty common sight, and that I don't think that is unique to Iowa. Pretty much any state I've been in, there's been problems with silt fence, and they build up, and the pressure from sediment and then holding back the water, the hydrostatic pressure is just too much for these materials, and they end up failing. And so what happens to all that sediment that's captured behind the silt fence? Well, the next storm comes through and that washes right off site. So we started talking about ways to potentially improve this. And so the silt fence was a geotextile material simply attached to a T-post, spaced 8 feet apart. And so our first modification that we started talking about was to close the spacing on the T-post just a little bit, decrease that spacing from 8 feet to 5 feet, and then also have a 6-inch offset of the geotextile material before it was either sliced or trenched into the ground. Now, that offset allowed the material to stay trenched into the ground, and then your sediment-laden water would flow over top of it, and this prevented that material from dislodging from the ground. And this helped prevent any of the undercutting that might occur. Now, closing in that spacing with the T-posts, our T-posts were more frequently occurring, and thus we're able to stand up to the pressure a little bit more. So we saw a lot less failure, and you can see here our silt fence is filled up to the very, very top with sediment. And although this would still need to be maintained, there was no sort of T-post deflection or failure there on the silt fence. Now, another option we came up with was what some states call the heavy-duty silt fence. And this would be reinforcing our silt fence with a wire reinforcement or a chicken wire. The geotextile was then attached to the chicken wire just at one location rather than 3 pinned locations to the T-post. And you can see here there's a lot of sediment captured behind that silt fence. So this was all visually observed that we were really able to improve the structural integrity of these sediment barriers and capture a lot more sediment upstream. So just based off of these visual observations and also contractor input, we were able to adopt some of these installations. One of those being the offset, as you see here. So we actually were able to influence Iowa DOT standard designs based on the findings that we saw from this field monitoring effort. So depending on the location of that silt fence, we might vary the T-post spacing and close it in just a bit, and then include that offset that prevents any sort of undercutting or the geotextile being dislodged from the ground. The next catalog practice that we saw were those ditch checks, again here in the center line of this picture. And we were using predominantly silt fence, but also some occurrences of wattles and rock check dams. So these were the 3 major types of ditch checks that we were seeing on site. We relied very heavily on UAV photogrammetry, so did quite a bit of analysis with our UAVs, and then also just some regular ground survey. So just to go over what a ditch check is, we view it as both an erosion and a sediment control. So ditch checks are typically installed within a conveyance structure channel to reduce the flow velocity. These then reduce the erosive or the shear force within the channel. And they should also create slow impoundments that are favorable for sedimentation of our largest particles. Now, when we were on site, just like the sediment barriers, we saw a lot of downed silt fence. So they were using silt fence ditch checks, and just with the hydrostatic pressure coming through that channel and the high flow velocities, we were seeing these washed out. But also, we just saw a lot of sediment buildup behind them. So again, started looking into literature, what other states might be doing, and how we could improve the practice in the state of Iowa. So we field implemented various standard and modified ditch check designs to see how they would perform on our site. Now we did weekly inspections, looking at, again, visual observations, but this time we were also quantifying the rainfall that was occurring on site, and we were tracking channel erosion and sediment deposition with various surveying and LIDAR techniques. So the first silt fence ditch check that we looked at was the Iowa DOT standard at the time. This was just a silt fence that was installed perpendicular to flow within a channel. And you can see in this picture that there was certainly some sediment buildup behind the silt fence. But again, we got a lot of T-post deflection there on the center line, where our flows would be the most concentrated. And eventually, this caused that geotextile to pull out. And if you follow the flow path here, you can certainly see signs of undercutting. Now, if this was not maintained, then we could expect that this silt fence would eventually wash out. And that was the case in many areas of this site. So when we were tracking sediment deposition, we ended up getting just about half of a cubic foot of sediment, and that was after 12 inches cumulative of rainfall on site. Now, when we started looking at what other states are doing to be able to use silt fence in channelized flow conditions, we found some very unique installations. One being this V-shaped installation. Now, I want to add that the silt fence is in a V, but it also has that chicken wire or that wire reinforcement behind it to help with the hydrostatic loading. Additionally, the geotextile is cut down just a little bit at the center point so that the lowest point of the V is right there at the vertex, and that allows us to know where the silt fence is going to dewater or overtop. If that silt fence is full with sediment and water, we know that our flow will be coming right over what we're calling the weir right at the vertex. And that allows us to provide some energy dissipation right here so the flow can keep moving down or stair-stepping down that channel. So we have our V shape with some wire reinforcement and then a weir right at the vertex. And we were able to capture 2 cubic feet of sediment. And so that's, 4 times what we were able to capture with the standard. And there were no signs of failure or incompetencies when we were looking and comparing after the same amount of rainfall on the same site. This one was just installed a little bit further down the channel. So the next practice we looked at was also sticking within ditch checks, but looking at wattles. Wattles were really popular due to their ease of install on the site. Again, just installed perpendicular to the flow path and staked directly through the media. Now, if these were not installed properly, we saw a lot of signs of undercutting, and that's evident here in this photograph. If we look at, we have some sediment accumulation up here, but our flow is going down and we're undercutting that wattle, and that's evident based on the erosion within the channel. So we were able to look at the surfaces and again quantify how much sediment was being captured. And here we were just at about 1/10 of a cubic foot of sediment deposition. So wanted to see what we could do to prevent some of that undercutting and help promote that wattle staying anchored down into the ground and maintaining that intimate ground contact, making sure that we are impounding behind the practice. At the time, the Iowa DOT had a big push to use natural materials within the channel just in case they were left behind. So we took an Excelsior fiber matting and put that down in the channel. We were then able to sod staple the bottom of that wattle down through the netting into the channel, lay that wattle down, and then we used a TP staking configuration. Now, the stakes did not pierce the wattle at all. They were crossed in an A-frame, and that kept pressure down on the top of the wattle. So wattles are often, light natural fibers. Maybe they're straw, maybe they're an Excelsior fill, so they're very lightweight, and in high flow conditions, they can become buoyant. Now, with this TP staking, we're putting some pressure on that top, making sure that wattle stays down on the ground, even in high flow. And you can see here, we have quite a bit of sediment buildup and no evidence of that undercutting that we saw on the standard design. We were also able to get a lot more vegetation to establish in the channel downstream. Now, this provided 1.5 cubic foot of average sediment deposition after 12 cumulative inches of rainfall on the site. So we were able to capture with a 20-inch wattle almost what we were able to capture with the silt fence installation. So quite a bit of improvements there. So the 4 monitored installations, changing that silt fence standard to the V shape with the reinforcement, and then changing the wattle ditch check standard to implement a TP staking configuration with a natural fiber underlay to try to promote that ground contact. We were able to enhance sediment capture in this case by 4 times, and then with the wattle by nearly 12 times. And again, the DOT took these findings quite seriously and wanted to improve their stormwater management plan. And so we saw, again, another change in the design standards. And so certainly we went from that standard wattle to the modified installation doing non-destructive staking, including that sod staple and then the natural fiber underlay. At this time, the silt fence ditch check has not been modified, and that's due to looking at the additional costs with the other design components, including the wire reinforcement, and then also educating the installers and getting their feedback on if it would be feasible to install ditch checks in that V installation. So we applied various different design and installation techniques, and we saw quite a bit of an increase when it came to sediment retention. So modified practices significantly improved sediment capture when we did statistical analysis on these. And this is really important because on this site, it was a 12-mile-long DOT project, and over 3,500 ditch checks were included in the stormwater pollution prevention plan. And so when we compared how much sediment would have been captured had all of the ditch checks been improved, we were able to go from 4.5 truckloads to 18 truckloads of sediment being captured on the site with the modified silt fence. Now, when we did that comparison with the wattles, if we continued just using the standard wattle practice, 1 truckload of sediment would have been captured on site, whereas if we did the modified installations, we could have captured up to 14 truckloads. However, there was a question about the additional cost related to these design components. And so that was a very interesting question and one that we wanted to answer for the DOT. And so we were able to do a cost analysis looking at the additional material cost, also the additional labor costs, because again, more design components, it's going to be an increase in time when it comes to installing these practices. And we compared what that total cost would be with the volume of sediment captured on site. And we could actually see that the cost per volume decreased with our modified practices. Now, the next cataloged practice we found, and I had previously mentioned, were our detention practices or sediment basins. Now, the Iowa DOT had a very unique design that we were looking at, and they actually created sediment basins or detention areas within a conveyance channel. And the way that they did this was by creating a small earthen dam across the conveyance channel and running a riser pipe through that earthen dam for dewatering. Now, the earthen dam was armored with an erosion stone to prevent any erosion on the top or the back side of that dam. And there was a low point to serve as the auxiliary spillway. Now you can see what a freshly installed in-channel sediment basin might look like. And when I looked at this picture and saw it in sight, there were many areas of exposed soil. Again, we're in a conveyance channel, so we may have high flow velocities that could cause erosion within that channel. And so it would be really important to get these sides stabilized with some sort of vegetation or matting. Now, it was no surprise that over time, we started to see some issues. So our channel was eroding, our sides were eroding. We actually had problems with our dewatering risers becoming buoyant and being dislodged from their position and not serving as the primary dewatering area. Now, one thing in this picture you can also see is our earthen dam. Well, there's some other low points, not just through that auxiliary spillway, that's causing a lot of erosion on the back side of that dam. So our sediment loads were going to be even higher leaving the basin than what was coming in. And over time, this is what that looked like. Even with the dewatering riser pipe maintained and put back in its place, we were just getting overtopping on that dam in other locations, and the erosion was very, very severe. And so we field monitored these sediment basins. We first monitored a single sediment basin, both at inflow and prior to discharge off-site, and then also sediment basins in series. So this would be where one sediment basin discharges and flows into another for enhanced residence time and sediment capture. Now, in both cases, we were getting very little turbidity reduction. So turbidity being our clarity of water. And when we talk about turbidity, turbidity is much like golf. The lower the score, the better the water. So a lot of times our influent turbidities were in 10,000 NTU. And maybe after residence, we were getting about 100 NTU removal. In many cases during storm events, there was no turbidity removal at all. And these basins were quite expensive to install. Depending on where they were, the price was anywhere from $2,000 to $3,000 per basin per contract. And so it was a lot of money that was being invested for very little effect. However, when we started to think about the principles of detention practices and this design, we did see that there were several benefits. One being that they use existing site infrastructure. Another being that the length to width flow path is increased, which we see from past literature that helps capture sediment and stored pollutants. Because we're already using existing site infrastructure, and these are long, skinny channels, we also have a reduced requirement for acquiring right-of-way on the side of our road, and all of this contributes to a reduced cost. Now, there might be site constraints that we can't do a traditional excavated pond, and being able to create a detention area in a channel might be beneficial. And so we wanted to see about ways that we could use this idea, but enhance it to also provide water quality improvements. So when we started to think about what makes an effective sediment basin, we knew that at the bare minimum, there had to be some sort of stabilized inflow channel, an area for settling to occur, a primary dewatering system that would allow the impoundment to dewater at a controlled rate, and then also an auxiliary spillway in the case that our settling pond was full or overflowed. Now, there are other components to a sediment basin that some states are using that definitely increase their effectiveness. One of those being baffles. These are the fences that you see going across the sediment basin. These help dissipate flow energy, which reduce turbulence or resuspension of previously settled material in the basin. We also have a surface dewatering system, such as a skimmer, and that allows the water to dewater from that top of the water column, which presumably is the cleanest or has had the most time for sediment to settle from. So we moved on to a second stage of this project. We did our field monitoring effort, and now we wanted to see the performance based on controlled testing. And so the second project was titled The Evaluation of Sediment Basin Performance Using Large-Scale Testing. This evaluated the standard and several modified sediment basin designs at the Auburn University Stormwater Research Facility. The first objective of this project was to develop a sediment basin that mimicked field scale and the hydrologic behavior of field-installed basins from Iowa. The second was to understand the sediment retention and the turbidity reduction in response to various sediment basin components or treatments. And then finally, look at the cost and developing implementable recommendations for the Iowa DOT. Now, as I mentioned, we were doing a project for the Iowa DOT. However, this project was going to be occurring at the Auburn University Stormwater Research Facility. Now, Auburn is based in Alabama, and so we wanted to make sure anything that we were going to do was mimicking the rainfall and runoff situations that were similar to that of Iowa, and also using soils or sediments that would be representative of the area. Now, the Auburn University Stormwater Research Facility was previously the Erosion and Sediment Control Testing Facility and is housed right next to the National Center for Asphalt Technology. So the Auburn University SURF, as we call it for short, mission statement is to create environmental stewards within the construction industry by developing implementable erosion and sediment control technologies. The fun thing about Auburn Stormwater Research Facility is that you can mimic construction sites, but you're able to control the rainfall, the grading activities, and all that's going around your practices. Now, when we started looking at how to evaluate a sediment basin or what components we wanted to include, we came up with this testing regimen. The first would be to install a standard sediment basin following Iowa DOT guidelines, and this would be unlined. Now, the challenge here is that in Auburn, we have a different soil type, and so we were going to have to be dealing with that. If erosion occurred within the channel or within the basin, how could we make comparisons? And so this first area, we looked at the standard basin using Alabama soils. The next thing we did was line the basin to provide stability of that channel and also the sides of the basin with a geotextile lining. We repeated that testing with Alabama native soils, and we could make the comparison of what was happening between an unlined and a lined basin, showing what would occur if the basins were stabilized. The next thing we did was repeat that testing, except this time we were introducing soil shipped straight from Iowa. And so this allowed us to make the comparisons between the two soil types. Now, once we switched to Iowa soils, we stayed that way. So we then evaluated that surface skimmer, as I mentioned previously, porous baffles to try to dissipate some of that flow energy and velocity, and then also a forebay. We created a forebay by installing a rock check dam upstream, and the forebay would capture our rapidly settable solids or our largest particles such as sands that settle very quickly from suspension. We looked at each of those treatments individually, but before determining what the best system or the most feasible and effective installation would be, and that's our MFEI. So MFEI we evaluated as a system. Once we did that, we added what we call flocculant, which we'll get into just a little bit later. Now, we introduced flow into the basin for 30 minutes, And then the basin dewatered for 4.5 hours before reintroducing flow again. This second period of sediment-laden flow introduction was to simulate what would happen if a second storm event came through when there was already some volume or some level of water within the basin. We repeated this testing 3 times for repeatability, and we were able to find some really exciting results. So our basin was 200 feet long and about 40 feet wide at its widest point. You can see here the earthen dam that would be constructed to create our basin area, and then where a riprap check dam would be to create that forebay in later testing. We constructed that basin according to Iowa DOT spec, and you can see here our riser pipe sticking out. This is on the downstream end of what would be serving as our auxiliary spillway. Took a survey and we were able to get our base case scenario that we would compare to later for sedimentation and also any erosion patterns within the basin. Now, as I mentioned, we wanted to be able to mimic the hydrology and also the sediment loss that might occur on an Iowa DOT site. And so we did some GIS analysis to come up with our flow and our sediment introduction rates. So we were introducing flow at 1.7 cubic foot per second and sediment at 62.7 pounds per minute. And this was simulating about 1 acre, just a little bit less than 1 acre of a drainage area that would be captured within the basin. My favorite part of this project is that I had to order 5 tractor trailer loads of soil right from an Iowa DOT construction site that was shipped down to us in Auburn, Alabama. So the soil was taken from various different areas. So when it got to us, we dried it out and tried to mix it up to make it as homogeneous as possible. So this is our sediment basin area. This is an aerial shot. So we have our 200-foot long basin with its widest point being here at dewatering. You can see our riser pipes sticking up and then our auxiliary spillway. Up at the top, we have our flow and sediment introduction apparatus. We monitored various different parameters, including flow rates, basin stage levels, and then water quality parameters, including total suspended solids and turbidity. We used various different instrumentation, including automated samplers for our water quality, which is what I'll be talking about primarily in the next few slides. So as I mentioned, some of our treatments included lining, a dewatering surface skimmer, baffles, and a forebay. And as you can see here, the sedimentation patterns between these all look very different. And when we started talking to the Iowa DOT about what would be feasible for them, they really liked the idea of stabilizing the basin, implementing surface skimmers that would be quite easy, and then just putting in a rock check dam and covering that in geotextile to create the forebay area. However, the baffles in the basin were difficult to install and a little troublesome to try to maintain or dredge out, and so they didn't see this being as feasible to implement on site. So when we evaluated our system, we removed baffles but kept the lining, surface skimmer, and the forebay. So when we started to compare sediment retention, we were able to get individually with the skimmer 88% sediment retention. So that means 88% of the sediment introduced was retained within the basin. When we installed a forebay, we were able to get 89% retention, and with baffles, 84%. And so because the baffles were lower and they were difficult to install and maintain around, they were not included in this system. Once we created the system, we tested with and without flocculant. If you're unfamiliar with flocculant, flocculant is applied typically upstream of sediment basins, and they act as a glue. So they're able to get our finest particles, like our clays, to stick together. This creates larger particles that are able to settle from suspension much quicker. So here is our MFEI, our system. So we had our geotextile lining, we had a forebay, and then our skimmer was at the very end. When flocculant was used, we just used flocculant blocks that were very simple to install, put right in the flow path so that sediment-laden water passed over them and had time to mix and cause those particles to bind and settle from suspension. Now, as I mentioned, one of the parameters we looked at was sediment retention. And so I spoke just a little bit about the sediment retention that we were able to achieve with individual components, but I want to highlight these top two rows here. The MFEI, so that included the forebay, the forebay, skimmers, and lining. We were able to get 96% sediment retention. So that's quite a bit of sediment retention. Now, when we added flocculant, we were able to increase this to 98%. So that means that 98% of the sediment that was being washed these basins was retained, and only 2% was yield, or what would be discharged from the site. So we were able to increase that from our baseline of 76% all the way to 98%. So very significant when it came to sediment retention. And when we started looking at water quality, looking at patterns of total suspended solids, turbidity, we saw very similar results. And so each of these lines represent the turbidity at discharge. We monitored very closely for the first 2 hours, looking at every 2 minutes taking a sample. We also looked at extended dewatering over 48 hours, which was the current standard to dewater the sediment basins. Now, one thing I want to point out is that we are up into well above 2,000 NTU for just our lined basins. But when we implement all of these other components as a system, we're able to get to 250 NTU and drop even below 100 NTU during that extended dewatering period. Again, our lower turbidity meaning better water quality. Now, when we apply that flocculant, we're able to drop very rapidly, even during the filling period. So that would indicate that during a storm event, if flocculant was used with all these other components, we may be able to reach any turbidity effluent limits required. So we're well under 100 NTU. So we're able to achieve that very, very rapidly. And so when we look at comparing the system with flocculant, we were able to reduce the turbidity by 42% when flocculant was applied. So almost reducing the turbidity by half just by putting in some of those flocculant blocks upstream. And what this graph is showing is looking at the particles that were captured in the basin. And so the solid lines represent just using the basin as a system with those various components. And the dotted lines represent when flocculant was also applied to that system. Now, this general shift to the zero axis is showing that the particle size is getting smaller. So when we use flocculant, we're able to capture those very fine clays or silts that we typically aren't due to their settling velocities. So when we put the whole system together, we were able to get 96% sediment retention. However, when we use that system with flocculant, we could increase the sediment retention to 98% and improve turbidity reduction and the particle size by nearly half. So basically, flocculant allows our finest particles to settle much faster, and this creates a potential to be able to decrease that detention time or volume required in our sediment basin designs. Flocculant might also help us achieve any numeric turbidity limits. There is some concern around residual flocculant concentration. So, flocculant is this chemical. We're trying to keep chemicals and pollutants away from our waterways. If we're putting in flocculant, are there going to be downstream impacts? And currently flocculants, it varies on the type, and so that could be a whole nother presentation. But there are very minimal downstream effects with the flocculants that we were using. Discharge concentrations were much below 10 milligrams per liter, and there's really no harm until you get above about 30 milligrams per liter. And so the way that these are being dosed and being used, we're really improving that turbidity, which helps the health of our receiving waters and also be able to help our aquatic life when it comes to site feeding and reproduction. So these are the main findings, and right now the Iowa DOT is going through stakeholder surveys and feedback based on sediment basin designs from this research. So this research just completed in May of this year, so we would expect to see another design modification or change from the Iowa DOT as a result of the research findings. So that was a lot to take in, but if there are any questions based on the research or how we are implementing it, I would be happy to answer.
Wow, what an interesting study. And thank you so much for sharing that information. That's really interesting. I don't see any questions in chat just yet, but of course, as Jamie mentioned, if anyone wants to ask her some questions, now would be a perfect time. As a reminder, while we're waiting, if anyone would like to receive a certificate of attendance for today's presentation, please send me an email to request it. We ask that you don't request those in chat because we may not have your email address linked to your username on Teams. I should be able to get the certificates out today, but if not, it'll be early next week. I think Chris, yes, good. And as we've mentioned, a recording of today's presentation should be available on our website in the next few days. Chris is going to put that website link into chat for you now as well. Oh, we had one comment, not a question, but Michaela says these projects were really cool to hear about, and I would agree. Thank you,
Well,
Michaela.
thank you. I'm glad you're happy to hear them.
I think Chris has a few words for us.
Yes, if anyone still needs to register for any of our newsletters, I'm going to share that currently on our screen. Please reach out to Rebecca and she'll happily get you the information. You can also sign up for our newsletters and training announcements now by pointing your cell phone's camera at the desired QR code or codes. Each QR code is a link to a specific newsletter. The only way you can sign up for either the construction or the industrial training and education announcements is with these QR codes or a direct link. The Stormwater Quality Newsletter is the only one listed on the Gov Delivery website. Again, if you have any questions about our newsletters, please email Rebecca. Also, be sure to sign up for next year's webinar series.
Right, so we've got a couple more comments. Matthew says, thank you. Nick says, great presentation and go Pokes. Yeah. And Derek says, excellent presentation as well. If anyone does have any questions, Jamie, would you mind hanging out for just a few minutes on here?
Yeah,
Okay,
happy
great.
to.
Oh, Jacob says, thank you. Hope to see this research implemented in Oklahoma and continued at OSU. Excellent. Well, thank you all for attending today's session. We hope everyone enjoyed the presentation and this year's webinar series. We hope to see you again next year for the bi-monthly webinar series starting in February. We will also have several lunch and learn opportunities that we will be announcing throughout the year. Have a great afternoon and happy holidays.